In this video, I'm going to introduce the tangent line. Tangent line is different from a secant line in that it's only going to intersect or touch your function or curve at exactly one point. Tangent actually means to touch, so a tangent line is just touching a line only once. And then what it's going to allow us to do is find the slope of a curve at a specific point. If a tangent line is touching a curve at a specific point, then the slope of the tangent line is going to represent the slope of that curve at the exact same point. The slope of a tangent line is really representing the instantaneous slope or the instantaneous rate of change of a function at a specific point. And that instantaneous rate of change is what we call a derivative. And the derivative has a lot of different interpretations or a lot of different definitions. This is called the limit definition of a derivative. And we talked about the difference quotient in a more recent video. We'll see this diagram really showing us how h is approaching 0, or this change of x is approaching 0, which is allowing this difference quotient to represent slope. So though this animation is starting off by showing a secant line, it's got two intersection points, and then as this change in x is getting smaller and smaller, or as the distance between those 2 points is getting smaller and smaller, we're approaching this single point right here, which then turns into a tangent line because it just touches the function at one point. So a little transformation from a secant line to a tangent line, showing you that that change of x, or that distance between those 2 points, is shrinking, shrinking, shrinking as it's approaching a zero change, and giving us this limit definition of a derivative. In a previous video, we showed how we could use that difference quotient to find the slope, or the instantaneous rate of change at a specific point. We're going to use that technique to write the equation of a tangent line. To write the equation of any line, we need a slope and a point. So we'll be able to find that slope by using the difference quotient, and then we'll be able to write the equation of a line by using the point given to us in the problem. So again, using that difference quotient, it's helpful if you evaluate that x plus h input first. So plugging in x plus h into this function means I'm plugging x plus h into this input and x plus h into this input and evaluating. So x plus h squared plus 2 times x plus h plus 1. Break this apart and FOIL it, or distribute it. Distribute this 2 inside of there, and we end up with x squared plus 2xh plus h squared plus 2x plus 2h plus 1. Big long expression there. And we plug that into that f of x plus h spot. We're then going to subtract the original function. So that original function right here is becoming substituted into this spot and subtracted. Make sure that if the function has more than one term, that you distribute that subtraction or that negative throughout, and that makes everything in your function the opposite of what it was. So instead of minus x squared plus 2x plus 1, we get minus x squared minus 2x minus 1. Let's combine some like terms, and we'll be able to simplify this monstrous expression right here. X squared and negative x squared are going to cancel and go away. Positive 2x and negative 2x are going away, and positive 1 and negative 1 are going away, which leaves behind 2xh plus h squared plus 2h, all divided by h. We still can't substitute our 0 and evaluate the limit yet until we get rid of this h. So on the top, all of your terms have an h. Let's factor that out, leaving behind 2x plus h plus 2. Cancel your h's, and then you're finally left with 2x plus h plus 2. Now we can evaluate that limit as h approaches 0 and plug a 0 in for h, which gives us our final slope equation, which is 2x plus 2. This is also called the derivative of the function. It's representing the slope at any point. All we got to do is plug in an x value to figure out the slope at that point. So originally in the problem we were told that we wanted to find the slope at x equals 1. Now we can finally plug 1 in for x and find the slope is 4. So it's a positive slope, positive rate of change, so the function is increasing. Now that we have a slope, we can finally write the equation of the line, but we need a coordinate pair or an input and an output at a specific point. We were told that x equals 1. We wanted to find the output of that. We just plug it into the original function, and that way we get our output based on our input. So if I plug 1 into my function, 1 squared plus 2 times 1 plus 1 is 1 plus 2 plus 1, which is 4. So now I know my coordinate at 1 gives me an output of 4. I know a location on my tangent line. This is exactly a point that's sharing the tangent line and the function. That's that intersection point. So now we have a point and we have a slope. We can finally use our point-slope form and write the equation of the line. We're plugging in our coordinate. Y value was 4. The x value was 1. And our slope was 4, we figured out earlier. So the y value, the slope, and the x value get substituted. We could leave it in this form or simplify it and put it into slope-intercept form. Just add 4 to both sides, distribute 4 times x and 4 times negative 1. And these 4's are going to cancel, giving us a simplified linear equation, y equals 4x. So if we look at everything that we just did, we had this original quadratic, x squared plus 2x plus 1 in red. We came up with a tangent line that intersected it at 1, 4. And that tangent line had a slope of 4, which is telling us that the slope of the curve of that parabola is also 4 when x equals 1. But just at that specific point, as soon as we move away from that point, our slope is going to change. And we can use that slope equation that we came up with, and 2x plus 2, to evaluate the slope really at any point on this parabola. If I plug in negative 2, I can evaluate the slope at that point, and so on. So that's how we can use the tangent line and its slope to evaluate an instantaneous rate of change, or the instantaneous slope, or the slope at a specific point of a function, also known as the derivative.